Hello and welcome. In this video, we'll be considering stretching graphs and how the shape of graphs change when we have a stretch factor. Now, if I send you back a few lessons back where we started this chapter, we had an exercise where you had to plot or figure out the equation of this curve here, this cubic curve. And remember, what we said is that you have to deal with something called the stretch factor. What was that? There was some function that once we figured out the equation, once we multiplied out x plus 2 square and we multiplied with the other factor of x minus 1, and then the equation kind of didn't work out, and I said we need to figure out this k. So the stretch factor here in that case was outside of the function, right? Okay, so if I out the equation, I don't remember exactly what it was. It was x cube, x square. It didn't have x square. Doesn't matter what it was. Now this this stretch factor, we're gonna talk about it in more depth in this video. So let's look at this example here, and this original function is x squared plus 2x, right? And so I'm just plotting, finding the values for the original function. So this is just a simple calculator exercise. And if we plotted the original equation, it would have had a root at, if you factorize it, it has a root at 0, and the other root is at minus 2, because it factorizes into x and x plus 2. So that's not a surprise that the graph looks like so, and the y-intercept is at 0. Now we have a stretch factor of 2. Notice this 2 is multiplied outside of f. Therefore, after we evaluate f, we do everything with x's, then we multiply it by 2. Okay, so let's figure out what the values of new value y value is going to be. What you notice is that these blue numbers are double the red numbers above them. All right, so we took that 15 times it by 2, we would have got these numbers, the blue numbers. So what do you think the new graph is going to look like? Because it's the stretch factor is in y direction, it's outside of the bracket. I've expressed this many times before. So outside of the bracket affects the output ordinarily. Okay, outside, we mean y, and in y direction ordinarily. So here, because it's a double and it's a plus 2, when the y values are negative, they're going to become more negative. When we double them, this minus 1 y value becomes minus 2, and so on. When y value is 0, it's going to remain at 0. Okay, so the roots of the equation aren't going to change, but it's going to get stretched. You just imagine that if these 2 points are fixed, we're going to fix these 2 points where y is 0, and then we're going to stretch it in the y direction. So it will look something like so. If when this point y value was was it a 3? Yeah, it was a 3 here, is doubled to 6 now. Okay, and this point that was 8 will have moved up to 16. Now let's see, there is another kind of a stretch factor, which is, you don't call it a stretch, but you rather call it a reflection. When you put a minus 1 in front of the function, all right, or any negative value, it will reflect which values? The x values or y values. Because this minus 1 is outside of the function, affects the output, that is y values. So let's try to picture the negative f of x in this situation. That means instead of this minus 2, we'll have a minus 1 here. Let me get rid of my previous writing. So we'll have a minus 1, or minus multiplied by this bracket x squared plus 2x. So everything will turn into negative. You'll have a negative x squared minus 2x. Now you don't have to plot a new table here. All you have to think about is the y values are going to flip. That red line there is going to flip in x-axis, okay? So this point will be there. Its corresponding point will be up here. When it has a root, then it has a root at 0. That's fine. Now the red line was at positive 3 and minus 3. So that would now turn into this coordinate and this coordinate here. So the negative f of x will have a shape like so. It will reflecting x-axis, okay? Notice the mirror line is the x-axis of y equals to 0, right? So the reflection, this is the graph for this function here, negative f of x, right? I hope you understand that reflection is a kind of a stretch, because you could have a minus 2 rather than a minus 1. So we count reflections as kind of a stretch factor. Alright, so let's look at the next next stretch. This time, this is transformation that's happening inside the bracket. So we call this a stretch in x direction because it will affect the input values, the x values. So now when you first double the numbers and then apply the function, that's what it means. The 2 is inside the bracket. So first we take this minus 3, we're going to times it by 2, and then we're going to square it and add 2 lots of it to itself. So we end up with 24 anyway. You can use... Alright, so I'm just going to show you the outcome here on the graph, and then we discuss it. What you notice is that the original root was at minus 2, but it's actually halved and become minus 1. When it was 0, then halving 0 is still 0. When this x value was a 1, or sorry, the x value is here, is a 2, when it's halved, is going to x goes to y, 1, and the y value remains as it is. When the x value here was a minus 4, alright, it's halved, and now it's at minus 2 here, alright? So I'm talking about halving when actually the number in front of the x is a 2. Remember, inside the bracket affects input inversely, alright? So it has the opposite effect. Even though the x values are the x values halving. I'll try to explain it with a straight line equation here. Let's say we have a straight line of x minus 5 here. I've plotted this graph so that its intercept is at minus 5, and if you notice the gradient is 1 here. Now if you try to write the equation for this g of 2x, that means wherever you have a x, you're going to have to double it. Now just go back and think about what would you do when you were year 9 and you were asked to plot this graph here. You would start with the intercept of minus 5, and you have a gradient of 2. So the gradient of 2 means that it will be twice as steep, right? So the new line for g of 2x, it will be twice as steep, isn't it? So when it's at 5 here, it would have to cross this point here, because that's 10 units further up. Now about it, what's happening is that the x values, when the gradient increases, when we're putting a 2 in front of the x's, we are increasing the gradient by a factor of 2. And increasing the gradient means that whatever this 5 was, the it's the x value is now at 5 over 2, right? That's why the values of x half actually when we increasing the gradient. This point here was x equals to 2 and now has half to x equals to 1, right? So x is 1 here and so on and so forth. So I'm going to change my pen color and consider g of half a x. Let me draw this one in purple or rather blue. I like blue. Half a x, if you think about it, if I go and look at g of x, I'll take the x value and I'm halving the x value and then subtracting 5. Okay, so halving means that the gradient will be shallower, right? The y-intercept is still at -5, but where it was crossing the x-axis at 5 is going to be at 10. So the new line here is shallower, isn't it? The gradient is a half, therefore x values double. All right. So notice, even though when I'm putting a half in front of the x, actually x values graph double. All right, times by 2. So that means I'm timesing them by 2. Right? It's the opposite effect. That's why I said inside the bracket the change affects input or x direction in x direction inversely. All right, so I hope that helps you remember what's going on. Just summarize what we talked about. We said when a stretch factor is outside of the function in front of the f or any other function, it counts as outside. It affects the values vertically or in y direction. All right, that's another way of saying y direction. When the stretch factor is inside the bracket, the scale factor of change is actually 1 over a. That's affecting the x values. That's another way of saying in x direction, horizontal, by a factor of you multiply them or you divide them by whatever that value of a is. Okay, so let's look at some other graphs. Let's say f of x is given to us. In some cases, they don't tell you what the function is. They just say, give you a few coordinates and say this is f of x. Now we have to plot f of minus x, and then I'm going to change my pen color and draw the other y is negative f of x. So let's see what we have here. The coordinates that we are told is 0 and -2, and we are now plotting the f of minus x with the blue line. So we are saying here that x values will be multiplied by -1. All right. So if you think about it, now we're considering a reflection of x values because they just multiply by -1. This -2 will end up to be a positive 2. 0 times -1 is still 0. So it will be reflected in the y-axis, all right? So where x equals to, this is the line of symmetry for this kind of reflection. We hadn't had a look at the reflection in y-axis, right? So when the minus sign is inside the bracket, reflection is affecting the x values, right? Inputs are reflected. Now when the minus sign is outside of the function, we said it will reflect in where y, in the y line being mirror line being y equal to 0. So this red line is going to be now, if I change my pen color to green, is going to be reflected in this green line, and therefore this point here will be further up here somewhere, and this point will be fixed, this point will be fixed, the roots of the equation will be fixed. We get a shape like that, like so. Okay, so one more time. Have a go at this exercise and then I'll show you the answer. So what does 9 minus x squared look like? You'll have an intercept of 9 and it look like a sad face like so. You can figure out the roots as well when you set x equals to 0. So then, sorry, y equal to 0. Alright, so now we're going to have to figure out what's y of 2x. The factor that the is 2 is inside the bracket means that it's going to make the graph steeper. So the new values of the roots will actually half. This will be 3 over 2 and this will be negative 3 over 2. These are going to be new roots. The y-intercept remains unchanged. It will still have to stretch up to 9. When x is 0, still the y-intercept remains as it is. So that's part A. Let's look at it. It's going to plot it here, down below. And now the next part, or I've flipped my pen color. So 2 is outside of the function here. Therefore, it will affect the outputs or the y values. It will stretch them ordinarily by a factor of 2. So the roots will be fixed at minus 3 and 3, but this y-intercept will go up to what? It will be 18. So it will look something like so. Okay, so we know from factorizing the difference of two squares that the roots are plus 3 and minus 3. Okay, I hope you found this helpful. There's one more question here. So we are asked to sketch this original curve here with roots. What are the roots here? One of the roots is 0, the other root is at 2, and the other root is at minus 1. This is a positive UV curve because all the coefficients of x are positive. So it will look something like so. I'm not drawing it very accurately here, but it will have the lowest uh, the, the lowest root is minus 1 and then 0 and then the 2. So actually it better be looking like this more here. So when we asked to sketch for part B, you notice that all the x values are doubled. Alright, what does that 2 do? This is like f of 2x, where you have a gradient of 2, right? So that would make the graph steeper. So this graph, if I change my pen color and draw the new line here, this this new graph will actually, the roots of the equation will half. Okay, when we make a graph steeper, it will get closer to the y-axis. All right, it will have this kind of a shape where it would go up to the same y values, but it will be closer to the y-axis. You kind of like x values half, right? So wherever this point was has moved to half its original point. So now it's at minus a half. The new root is at minus a half and a 1. And when it was 0, then it remains at 0 because so that's it. This is the original curve, and the new curve will be, let me get rid of my writing here. So you see that the roots will half, minus a half and 1. Now, when you have under in question part C, you have a negative of the function. All right, imagine all these roots here, the x's are have still positive, but outside of the function is a minus sign. So this red line will be reflected in the x-axis. It will flip upside down. The y values will flip. Okay, so let's look at that. In the green line here, you see the the shape of the graph remain. The roots are still at where they were, and the y values flip. Okay, so in this next exercise, first of all, maybe you want to make a note of this table here. This is a translation. We already talked about this. We talked about reflections inside of the function. Inside of the function, changes are made inversely. Okay, and we talked about outside of the function affecting output ordinarily, and this is a translation effect, this is a reflection effect, and this is a stretch in vertical direction. So now in this exercise, you've been asked to that you've been told that the original function is 3x plus 2, and that's the equation of this black line there. And you've been asked to write the equation of the transformed function and then match them up. So when the 2 is inside the bracket here, that means that take the x value and double it. So really, if I write it down here, there's more room. So f of 2x means that take that 3, wherever the x is, put the 2 in front of it, and close the bracket and then add 2. So my new function will be 6x plus 2. Now you can find the graph for that. For part B, have a go at this and then compare your answer with me. Pause the video and have a go. Alright, I hope you have tried it yourself. When 2 is outside of the function, that means that we're gonna put a bracket around 3x plus 2 and multiply it by 2. Alright, so the new equation will be 6x plus 4. Right? Notice the difference. Change inside the function, outside the function. For part C, I hope you've had a go at this. X values will be flipped. So negative f of x, that's f of minus x, rather. So when you have a 3, you open a bracket and you just making sure the x's are negative and you're adding the 2 as it is. So we'll have a 2 minus 3x. That's a neater way of writing it. For part D, we have negative sign outside of the function. Therefore, we put a bracket around function. I'm going to write 3x plus 2 here and put the minus sign on the outside and then multiply out the bracket. I'll have negative 3x minus 2. Now you can match them up. I believe the one that's got intercept of 4 is that one. So that's for line C here. The one with the intercept of minus 2 is this one here. So that's A. The one with intercept of 2, actually this has a 2 and that has a 2. The one with the positive gradient of 6 is the red line with intercept of 2. So that's red line is line D. And finally, what's left over is line B here. And if you check, line B has gradient of minus 3 and intercept of a 2. Alright, so it makes sense. Okay, so that was that. We just had a go at this question. There are some exercises here. Maybe you can try it for yourself, and then you'll figure out whether word shift really should be translation. If they ask you in the exam what is the transformation, don't say shift, say translation. Translation. Okay, shift is not the official word in mathematics, but we use it now and again. Alright, have a go at this exercise and I'll see you in the next video.